a representation which is collection of points joined by triangles, right? Which is representation, you see that when there is a connection of the two triangles, right, there is an issue of continuity, because between the two triangles you have an edge which would give you only a certain type of continuity or smoothness, right? And we will discuss those issues later in more details. So in order to be able to have a representation, so this is typically used for irregular shapes, shapes which are not generally of the type as we have seen in the first case, like cylinder and disc. These are typically the shapes of irregular types, irregular surfaces. In order to avoid or in order to incorporate higher degree of continuity, which I just mentioned about the limitation of the triangular mesh, there are surfaces which are parametric surfaces and can have higher order of continuity, right? They can have continuity which preserves the curvature or continuity of a second derivative. And these are parametric surfaces, and what you find that the surface which you get, or the shape which you get, is visibly smooth, right? Contrary to what you would observe in a triangular mesh. So we are going to discuss that also. And then you have another sort of a representation which is an implicit representation, which is also coming through an analytical description of the surface. For instance, sphere, which could be represented as f of x, comma y, comma z equals to 0 or constant. And you try to define that mathematically represented surface, where what you are saying is that there is a notion of field which is defined through f of x, y, z equals to constant. And depending on what you define that field as, you can actually have variants to that shape. So a sphere could have features as shown in this line. So these are implicit representations, and there are, pros and cons of each of these representations, which we may not be able to cover all of it, but we will try to see some of those in this tutorial. So this is with respect to what will happen in modeling. Though Professor Sharad Chandran is going to give the details of what would go on into the rendering, but let's say a sort of a gross picture of it would be somewhat that you would like to have once you have the shape represented in the form of a geometry. Render that which looks realistic. So this is trying to simulate what goes on into the process of rendering. So what you see is there is a camera which has an image plane onto which the scene which you are seeing through the camera getting projected on it, right? That's what you see as the transparent plane on it. So there are objects which are colored. You also see texture on the wall. You also see shades, which is a consequence of the interaction with the light source or light sources. You also see shadows, right? So all those components are actually part of rendering, and that's what you are going to see in the part of rendering. Then comes the third element, which is animation. So I'm sure all of you have seen computer-generated films these days. So how many of you have seen Shrek, for instance? Not too many. How many of you have seen Avatar? More than that. Okay. Well, see, both are computer-generated, but well, there is a principal difference in the two kinds. So what is going on there is once you have represented these models, you also need to add the movement and the dynamics to it. So this is just an example where this particular character may jump and make a movement, and then at the same time there could also be a movement which is a consequence of the movement of the camera with which you are viewing, right? So that would also add to the movement of the scene. So therefore, there are many aspects which need to be addressed when we talk about animation. So we will also discuss this element. So this is just for those who are just beginners, and this is not an exhaustive list, who haven't done any course in computer graphics, for instance. So these are the typical texts which are used in a course of computer graphics. And as I said, this is not a complete list, right? There could be several additions to it. So those of you who are interested in beginning this may refer to any one of these. Just to give you a very brief history of computer graphics, particularly for those who are just the beginners. So in 1963, we got the first graphics workstation due to Sutherland. Right? That's the first time we could see displays. Right? In 1969, we got first SIGGRAPH. So SIGGRAPH is Special Interest Group in Graphics, which got started by ACM, which is American Computing Machinery, in the United States. And in fact, it's considered the biggest event in the community of graphics. Publishing in SIGGRAPH is the most coveted publication anyone aspires for. And in fact, now we also have SIGGRAPH Asia. So SIGGRAPH, as it's an event by ACM, gets held only in North America. Now there is SIGGRAPH Asia, which is now held in the Asian continent. So now we have every year SIGGRAPH as well as SIGGRAPH Asia. So in early 1970s, in fact, the emphasis was on raster graphics, shading, illumination, and things like that. So the basic idea was, how do we make things which are realistic in looks. In late 70s, again, continuation of those aspects, texture mapping, ray tracing, that's what we are going to also see in the tutorial. Again, emphasis on realism in rendering, primarily the photorealism, right? Then aspects of animation where you could include physics into, right? The idea is that there are many situations where you can inject the physical laws to be able to make the animation more realistic. 1989 was the year when Tintoy, a computer-generated film from Pixar, got the Academy Award. And in fact, nowadays it's sort of a common practice, right? And you see an award coming to computer-generated films more often than what it used to be. In 1990s, the scope of computer graphics enlarged, right? It was not just creating objects and be able to display them and move them. So in fact, machine interaction or computer-human interaction, scientific visualization, virtual reality, augmented reality, and so on. So the scope of computer graphics, in fact, became much larger. In 2000 and continuing, in fact, because of the acquisition of the data, which nowadays has become much easier than what it used to be in terms of the devices we have, the aspects of dealing with the data became important. Right? So you end up getting huge amount of data, and then you need to process that data before you can actually use it for the purpose of modeling, for the purpose of animation, for the purpose of rendering, and so on. Right? So data engineering aspects started coming into play while doing computer graphics. So that gives you sort of a very brief, gross level historical perspective in computer graphics. So now let me focus on what the first part of this tutorial is going to be, which is on modeling, focusing on shape representation and design. Any questions so far? Okay, so these are the items which I'm going to look at, right? First, there will be some motivation as to why are we interested in geometric modeling. Then we will see specific representation of shapes, both parametrically while designing curves and surfaces. And maybe, if time permit, I will also talk about a little bit on mesh, and the 3 points which I have mentioned would be covered only if the triangle is perfect. Right, so that's basically going to be the focus. Okay, so one of the things is when we talk about shape representation, right, it's always an inspiration of what goes on reality. Right? So when we want to do, for instance, animation or anything using synthetic objects, for instance, in this case, there is a horse, right, and that's what we want to model. And here, when I refer to modeling, I am basically talking about shape and the geometry modeling. So what you may have is to be able to have a three-dimensional representation of it. The points which are going to take the x, y, z, position of the various sample which is giving you the envelope of the shape for the horse. Right? So that's the first thing which you would need. Right? And subsequently, once you have done adequate sampling of those positions, you would like to connect to be able to have a surface which is defined through those points. And then, there are many different reasons why would you like to define a surface through those points. Right? You could, perhaps, once having acquired those points, render those points themselves. Right? And that's what gets covered in point-based rendering. However, there are lots of other things which you would not be able to do so conveniently if you're just doing point-based rendering. And that is why this step of getting from the point samples which you have, you go to the meshes. Right? Okay. Why 3D objects, 3D models? Well, there are several reasons, and I think I don't necessarily have to motivate you. You have games. I'm sure many of you have played games of different kinds. Architectural design. These days, everything is done in 3D. Right? So you need the modeling tools and the representation of the models in 3D. You have the example of Google Earth, right, which gives you a complete 3D description of the models. Movies, as I already mentioned. Engineering, in fact, whenever you want to do the analysis of the design, what goes on in terms of the stress and the strain analysis, you may require three-dimensional models. Medicine, that's also a possible application. Once you have done the modeling, 3D modeling of these shapes, it becomes easier for the clinician and the trainer to see for the purpose of diagnosis, for the purpose of detection of abnormalities and so on. Right? So there is a variety of applications where you would need 3D representation of objects. Right? And there are several ways in which you can do it. Right? One of the simpler ways is, well, the way a sculpture does. Right? So basically the idea is, you should be able to have a tool which allows you the flexibility of designing these 3D shapes as you would do as a sculptor. Right? So this is one of the examples. Here what you're doing is you're basically trying to manipulate the points and the surfaces which you have of the model the way you would like them to. Right? So there's a lot of user interaction which is going on. Underneath, of course, you have a representation which supports those manipulations. Right? So if you want to drag something, the surface gets dragged. Preserving the properties what you want. For instance, you may want to preserve certain continuity. Right? So that will get preserved. Right? So that goes on into a modeler. Okay? So that's sort of a forward way of doing modeling, right? Because you may be starting from scratch, for instance. You may be starting from, let's say, a sphere, right, or any other simpler shape, and then tweak those parts of the sphere and come out with a model like this. Okay. So I refer to that as a sort of a forward modeling, but you can also think of doing sort of a reverse. right? You may have a model, okay? And that's what many of the capturing devices offer, that as a ability. What you're really doing is you're trying to get the position of a model in 3D through one of the devices. So the scanner is what that acquisition device is, which eventually gives you 3D geometry. And as I mentioned in the beginning, this may have two-stage processing, which is that you may be first getting these sample points in 3D and then doing the connection of those sample points, creating the mesh representation of the shape. Right? And of course, while you are capturing the information regarding the shape, which is the geometry, you may also want to get the information about the color, the textures, and any other information which is relevant for this model. Okay? And so once you have done this geometry, then the rendering has to also take into, has to be accounted for, and you may be having a very realistic rendering of your model. For instance, you may be even adding features like fur, right, which is not there in the existing model. And that comes after the effect from rendering. Okay. Now, see, there are aspects of these representation which you may further need for these shapes to be functional, right? So you may have an assembling, for instance, as I mentioned in the beginning, that you may have a design of an engine, for instance, where your basic job is to do the shape design, which is coming as a consequence of different collection of primitives. And once you put them together, right, and which may require some mathematical representation, some transformations, to be able to have an entire scene, a complete object, then you have that 3D object functional. Right? So for instance, in order to be able to have this helicopter design, you may be having these wings designed separately, the body designed separately, and then you put them together. Right? Only then this becomes functional. Similarly, you may have a design of an architecture, monument, right? And that becomes functional once you have completed it. As this, again, a similar example which I mentioned for an engineering design and for a medical application, right? So you may have functional attributes also added to the representation of your 3D object, right? Okay. Though I mentioned that we are focusing on the representation of a shape, which is primarily talking about how do we specify the three-dimensional geometry of the object. However, you have to keep, as I mentioned while talking about the functional model, many different operations which would be facilitated by the process of your model. Right? So for instance, you may want to design a statue, right? But that statue may have more than just a geometry, right? Because in order to be able to have the statue or any other model which you are creating, the operations like the facility to edit, the facility to transform, making it smooth at different regions, right? To be able to render with the attributes you have, deform, animate, and so on. So you also have to have these operations in mind to be able to have a comprehensive model of what you are doing as a shape, right? So although in this part we are focusing in the specification of the geometry, but you cannot ignore the other aspects, right, when we talk about the comprehensive model. Okay, so now let's focus on the nitty-gritties, the details, right? So basically when we talk representation, you can see that, as I mentioned, you could have three-dimensional point data, which is nothing but collection of these points, which is point cloud data. It's a cloud of points which is in 3D. So that's a raw data. That's one way of getting your shape represented. And as I said, you may also have the rendering of those point cloud data to be able to display your 3D object. And then you also have, excuse me, the representation in the form of surfaces, right? And one example we saw, right, where there is a collection of points and you connect them, making triangular meshes on the top of that 3D points, and the parametric representation, which is what we are going to see more in details. And you may also have solid representation. Solid representation because, see, all the examples which we had seen earlier are only talking of the representation of the shape which is the envelope of the object. Right? We're not talking about what goes on inside. Right? However, most of the objects are actually solid. Right? So therefore, you also need to have a way to represent these objects as solid if there is such a need. Right? So you may have a volumetric representation which is in terms of what are called as voxels, which is basically 3D counterparts of your pixels. Right? So pixels are something which you're familiar to be able to represent an image. So voxels are similarly 3D pixels. Right? And you also have constructive solid geometry, which is analytical description of solids, right, which we have seen maybe in high school geometry, and to be able to assemble those solids to be able to create a 3D geometry of a complex object. Okay, so this I think we have already talked about. This is just to give you different examples of using the raw representation of point clouds. Okay. This is another sort of example where we talked about that having obtained the 3D points, you need to connect them and create these surfaces of the mesh. Because one of the things which you would actually see when we talk about rendering is that surfaces are required to be able to render the objects easily, right? So it becomes a requirement to be able to convert these set of points to the surfaces, right, or collection of surfaces. Of course, if the density of the points which you have acquired is fairly high, then you may need to process the data, right, either to reduce the density or to manipulate the density in a way that you can have different resolution representation of the object, so that if you do not need very dense representation of surface, right, you may just use a small set of points. Right? So that's what is happening here. Right? So this is a dense mesh and this is a relatively coarse mesh. Right? And you do observe that the inherent shape is preserved. Okay? And there could be mechanism where you can go from one to the other. Right? So you can keep that representation which allows you to go from one resolution to the other resolution. Right? So just for instance, that happens in the case of images. Right? Okay. The parametric representation. So one of the limitations that we discussed is that when we have mesh representation, because of the fact that meshes are meeting like a linear patches at the edges, right, has a limited continuity. And if I am interested in getting higher order continuity, I need to have a surface which allows me higher order continuity. And one way of going to that is using parametric representation. So in parametric representation, you may have some geometry which is being given to you, which in a way tries to capture the shape which you have in mind, right? But allows you to create the surface underneath which is of a higher order continuity. So for instance, these points which are mentioned here, so we will actually take this into much more details later on, but just to make the point, these points are given to you in 3D, just the way we created mesh, okay, which allows you to create a surface which is given through this bold line, which will be a surface of much higher continuity. It is solid, right? So this is just to make it clearer what I intended to convey through a voxel, right? So voxel, you see it as a three-dimensional grid, right? So all those points which you have are basically voxel, right? And that's why it's giving you a notion of a solid. Right? Now, this could be relevant in many applications, right? So you, for instance, you may also have a representation which allows you to have volumetric as well as surface representation, right? So from volumetric representation, you can go to surface representation, right? Which is just the envelope. So this becomes relevant, for instance, when you are doing medical imaging, right? So you may have a CAT scan or MRI images, which is nothing but a stack of it, and which you actually can view it as a brick, which is nothing but a volume, right? And if you are interested in doing a visualization of that volume, right, so you need to process that volume, okay, and be able to figure out different organs or different types of tissues in that volume, right? So that goes completely into the area of volumetric rendering, right? And I'm not sure that's what we are going to cover in the rendering part, perhaps not. Okay, so this is just giving you a sort of an example where you can, from the volumetric representation, extract the boundaries, right, which are nothing but the surfaces in that volume, right? So you have a stack of images. So these are one of the two of the images from the stack, and if you look at in the image, you would see the boundary, which are nothing but the contours of different objects, right? And if you join them together over the stack of images you have, you get the boundary of the surface, right? Which you can also apply directly to the volume. Now, the CSG, which is the constructed solid geometry representation, which I was mentioning as other way of representing these solids. So here what you have is, again, simple, primitive, solid, which are known to you mathematically. You have that collection. And by doing the appropriate operation and the manipulation of those primitive solids, you can create the objects which are interesting, right? So for instance, if you want to get an object of this kind, right? So what you can do is, you can perform operations of putting these two objects in a way that it gets assembled in this rectangular having a rectangle in between, and this cylinder which is just giving a hole to the one of the blocks, right? And if you look at the operations which you are doing, you're basically doing a translation of the blocks, right? Translation of the cylinder, okay? And you're performing union of these two blocks, right? Which is an appropriate translation, which is what is happening through this, right? This operation union, and then taking a difference onto this union of the cylinder, right? Which eventually gives you the object which interests you, right? So you can think this representation in the form of a tree, right? where the leaves here are nothing but the primitives, okay, and the intermediate levels are the transformations and the operations which are like Boolean operations, right? The difference, the union, and so on, intersection. So this is another way of representing shapes as collection of simple primitives. Okay, so the major chunk which I am going to actually talk will be on parametric surfaces, right? And before we talk about parametric surfaces, let's try to examine the curves first, right? Because whatever we are going to see in curves is perhaps can be extended to create surfaces. And that's the idea. Okay, so when I want to design a curve, right? So what is the best way of doing it? Well, or let's say what is the simplest way of doing it is that you do a collection of points and try to create a curve using segments of lines, right? Connect them together, right? Well, the only limitation remains is the shape which you get of the curve does not look smooth enough, right? You may want to have a curve which is like this, right? What you're getting is this. Okay, so this does not solve our problem, which is as a representation nothing but piecewise linear approximation of curve, right? It's basically collection of lines. So we go for higher degree approximations, right? So from linear approximation of the curve, we go to the higher degree approximation. And there could be various ways in which we can look at it. One way is explicit. So where you have a mathematical representation which is in the form of, for instance, when we talk about a representation in 2 dimensions, y is equal to f of x, right? So for instance, y is equal to mx plus c is a well-known representation of a line. Okay. Implicit form, this is something we have already seen, which is in the form of f of x, y equals to 0. So line in implicit form is ax plus by plus c equals to 0. Right? So you have representations like x square plus y square is equal to r square, x square plus y square plus z square is equal to r square of a sphere, and so on, right? So these representations are known to you mathematically. However, with the two, explicit or implicit, you can only have limited shapes, right? You can have spheres, cylinders, quadrates, and things like that. Maybe you don't have the variety of shapes which is of the kind of a free form shape which you may want to design, right? So this has a restriction in some sense. Now in the case of parametric representation, what are you trying to do? You're trying to represent the position which is in terms of x and y in the form of a parameter, right? So x is x of t, y is y of t. Okay. So that's what we are going to concentrate, right? We are not going to talk about the explicit and the implicit representation. Instead, we are going to focus on the parametric representation. Okay. And one of the motivation to have the parametric representation, as I mentioned, is to have the flexibility of having rich variety of free-form curves, right? Now, when we talk about the design of curves, right, we can actually look at the problem in 2 ways. One is that I may still be collecting sample of points, right, which is giving me a gross notion of what I want to have as a curve, right? And one way to say is that the curve should be passing through those points, therefore the curve is an interpolating curve, right? The other way of saying is that these points are only going to give sort of an approximation of the shape which the curve is going to have, right? So you can think of the design either as an interpolation problem or as an approximation problem, right? And I'm sure many of you may have heard the name splines, right? So splines are nothing but parametric representation of curves. Okay. So, in fact, historically, the word spline came from the design of ships long time back, where they wanted to have a free form of the surfaces of what you have the shape of the ship, the body of the ship. And what they really did, basically used a flexible sheet of a material and hung weights of different sizes, right? And they manipulated the weights and the shape got changed, right? So it was basically an adjustment of different weights which were put. So this is what is shown as an example, that you have this flexible sheet, right? And these are the weights which are put at different places on this sheet. And as you would change the position and the amount of these weights, the shape of that sheet is going to change, right? And that's the reason it got termed as splines. So basically that's the sort of a line diagram of what's going on here. Okay, so now let's talk about first the splines or the parametric curves which are of interpolating nature. Right? They are going to interpolate the points which are specified. The curve which is in space, 3D space, right? So I can represent cubic spline as a polynomial in the parameter t, which has a degree 3. Okay. Now, one of the advantages of using this is that if I take the derivative of this, right, which is p prime t, would be nothing but the derivative of that polynomial, right, with respect to t. Right? So that's easy to observe that I would get p prime t as this, right? Okay. So it will come in a minute why are we doing this, right? Why are we taking the derivative? Why are we doing all this, right? So now let's say I make a statement of the problem which is as follows. Given 2 points, right? Given the position of 2 points, which is represented here as P1 and P2. Also given the derivatives at these points, right, prime and P2 prime, I am interested in getting a curve which passes through P1 and P2, right, and also has the derivatives matching with the tangent vectors which is specified as P1 prime and P2 prime. Right? So this is a completely problem of interpolation, right? Trying to satisfy the boundary conditions which I have mentioned, right, in terms of the position of points and the tangent vectors. Right? Okay, so in other words, that's what we are looking at. So if I specify, let's say T1 equals to 0, then I am saying that P of t, right? P of t is my spline, or the parametric curve. P at 0 equals to P1. P at T2 equals to P2. P1 prime at 0 is P1 prime, right? And P prime at T2 is P2 prime. Okay. So how do we do it? Right? So this is the statement of the problem. Having seen the representation of the parametric curve in the form of a polynomial, right? Also knowing the conditions or the constraints which I need to satisfy for the curve. How do I get a curve which is an interpolation of these points, right, in the form of representation I just gave you. Should be easy. So what do I need to find out when I specify the parametric curve in terms of a polynomial? I need to find out the coefficients, right? Those capital B's, B1, B2, B3, B4. If I know them, I know the curve, right? Okay. So the problem basically translates to finding these coefficients. Okay, so basically say that I know what happens at P at 0, right, which is T1. If I substitute in the definition of my parametric curve, which is in the form of that polynomial, I get B1 as nothing but P1, right? Similarly, if I evaluate the curve at T2, that gives me this. Which equals to P2. Now I take the derivative of the curve, right, and equate to what I know as P1 prime and P2 prime. Right? So this sets up a system of equation which if I solve, I get these coefficients B1, B2, B3, B4, and that in turn gives me the parametric curve which I wanted to have, satisfying the constraints in the form of the position of points and the tangent vectors. Right? So that's an example of the cubic spline. Right? So that's what happens. Eventually you get, after having done the substitution and all, you can solve it, and this is what you get as the different coefficients. All right. Now, okay, so this is eventually the spline. Okay. Fine. Now let's say extend this problem. Right? What have we done? Given 2 points and the n tangent vectors at these points, I could obtain a curve which is cubic, right, satisfying these end conditions. Right? Now, if I have instead only 2 points, if I have n points, right, and what I'm interested in? I'm interested in getting a spline which passes through these points, right? And maybe there is some other constraint of satisfying the tangent vectors, right? So same thing if I extend to n points, right? What do I need to do? Yes? Any suggestions? Is the problem clear? Yes. You get what? Yes, see, it's already cubic spline, right? So I'm interested in cubic spline, which is of a higher order. But what I'm extending is from 2 points to n points.
Solve 3 n equations.
Pardon me?
Solve 3 n equations.
Solve 3 n equations. How do you solve 3 n
So
equations?
there are n points, and for each point you have x, y, z, right?
Okay. Okay, well, right.
So
And then
you solve. So currently you are solving equations, right? I mean, you are solving.
okay, so what you're basically trying to suggest is that I basically do this setup of equations for all the points. Right? That's what you're trying to suggest. Okay, fine. So before we go to n points, let's see if I add another point, which is 3 points, right? If I do that, perhaps I can see what happens with the n points. Right? So basically what we're saying is I have now 3 points P1, P2, P3 and their corresponding and tangent vectors, which are P1 prime, P2 prime, P3 prime, right? Now, the catch here is that P2 prime, which is sort of a junction point when I'm considering only two segments, right? That I should satisfy the continuity constraint, because what am I trying to do when I'm matching the tangent vector? I'm going to slightly higher order continuity, right? Matching the position is one continuity, which is what happens when we have these linear piecewise collection, right? If I match the n tangent vectors, I go one degree higher in the continuity, right? Things are going to follow the slope, isn't it? So what we can do is, and the other problem with this is that if I have these 3 points, see, I can either specify or reduce the tangent vectors at the two ends in some way or the other. But to be able to specify the n tangent vectors or get it from some other information may not be possible. Okay? So if I can figure out that, keeping the constraint that I want to have this curve smooth, I satisfy the condition, right? I satisfy all the conditions which I have. Okay, so that's what we'll try to do. We basically consider the specification of these n tangent vectors which are at 1 and 3 and see if we can find out the tangent vector at point P2. Okay, so see, I will probably not be able to prove this here, but what you can sort of get the idea that if I have a curve which is of a degree k, right? So for instance, if I talk about linear is not a good example. So let's say, keep this in mind, that let's say if I have a spline or a parametric curve which is having a degree k, right, then I can have k minus 1, right, the continuity of the order of k minus 1 at the junction point. So for the cubic spline, which is a third degree curve, would have at most second degree continuity, right, which would give you P2 double prime continuous over the joint. Okay. So the proof of it, this you perhaps can find in some textbook. So let me not get involved with it, but maybe we'll use this information. I can use for solving my equations. So I evaluate the second derivative at t is equal to t2, which is the junction point. So what I'm doing, I take first segment, figure out the second derivative at t2. I take the second segment, figure out the second derivative at p2, and then I have this equation. Right? This has to match. Okay. So this is giving me an additional information. Okay. Now with this, what I can do, in the system equations which I had, which were giving me the information about the position, which were giving me the information about the tangent vectors which are at the two endpoints, plus this set of equations for all the junction points, right? And then it becomes a matter of solving that system of equations, okay, giving you once again, the respective coefficients, the B1, B2, B3, B4, for each of the segments. Right? So it remains in some sense the piecewise spline, right? Because you're going to have splines for each of those segments. However, maintaining the constraints of continuity at the junction points. Okay. So I'm not giving you the entire set of equations, but the only thing which I would like to mention here is that you can represent the entire set of equations in the form of a matrix, right? Which is basically, so this is what your spline is, defined with the parameters u. F is nothing but some matrix, right? Which is going to take information about the different things which are known to you. Right? And G is the information which is geometric in sense. In this case, happens to be the position of points and the end tangent vectors. Okay. So eventually, what you get, the representation of the spline in the form of a matrix. All right. Yes.
Is it always possible to get higher order continuity?
Is it always possible to have
Higher
higher order continuity? Well, it depends the degree of polynomial you have chosen, right? In this case, we have taken cubic, right? So this will give you at most second derivative continuous, right? So if I had chosen quadratic, this would give me only up to first order continuity. Right? So, depending on the degree of spline or the degree of parametric representation in the polynomial form, you would get at most the higher order in respect to that order of the polynomial. Does that answer your question?
for cubic spline, in the last equation in the previous slide,
Yes.
there had a equality. So that equality can be true for any endpoint.
Yes, so what are we saying? We are saying that we are going to define the cubic splines for each of the segments. Right? Because what did we start with? We start with 2 points with their end tangent vectors. Right? And I could define a cubic spline between those. Isn't it? We extended that idea to be able to specify collection of splines for n number of points. Right? In this case, we only, to begin with, took 2 segments. Right? So, now the question becomes, for the junction point, what do I do? For junction point, we are saying that with the polynomial which I have, in this case, third degree, I can ensure the continuity for 2, right? For order 2, okay? So as a result, I have this constraint already available to me, which is in the form of satisfying the second derivative, right? And if the second derivative is matching, what are you going to do? The corresponding tangent vector which you get, right, is also going to match. Okay, so and so would be the position, right? So it's not that once you have the second derivative getting satisfied, your lower degree constraints are not going to be satisfied, right? Okay, so the basic idea is that if I want to choose, let's say, quartic, right, which is order 4, then I can think of even higher degree of continuity at the junction. Okay, but maybe I don't need that. So this is just to extend the idea of a cubic spline with n number of points, and keeping this constraint that my n tangent vectors also give me the condition of continuity, which I wanted to match, right? Because I don't want at the junction point having the tangent vectors different. That's pretty clear to me, right? And by imposing this constraint of matching the second derivative, I'm getting them, and they satisfy this fact that they will match. Is it clear?
My question was, if there is n point, we may not fit a cubic spline over that n points. I mean, it may not always possible. In that case, do we need regularization kind of thing to?
Why do you say that you would not be able to obtain a cubic spline with n points?
Is it always possible to get a cubic spline or hard degree spline over any n points?
Just see, you already are assuming to fit cubic spline with that data. Right? You're starting with this assumption that I'm going to fit cubic spline. Okay? You are not trying to fit any spline. You're trying to fit cubic spline. Right? That gives you certain constraints. Okay? Yes, any other question?
Coming back to your earlier equation,
Yeah.
you have four unknowns, B0 and B3. And for two, just point P1 and P2.
This one, right?
Yes, so you have four unknowns,
Correct.
and then how many? You have 8 equations to solve them?
So if I'm talking about the
You're equating the
X
C0,
of t,
C0 and C1.
right,
Assuming these are two-dimensional points.
right,
So I can get 8 equations of them.
that's correct.
And there are four unknowns. B1, B2, B3, B4.
No, see, what happens is that these also have the same dimensions,
So these are,
right? So the B's, which are talking as coefficient,
so there are 8 unknowns.
they are data. So they also have the same dimension as the representation of the curve. Okay, so if I'm talking about a 3D curve, then it has X and Y and Z. Any other question? Yeah.
In the figure you showed us, the animated figure, so that figure was represented by slides. So the comical character, grotesque character in that figure. In your initial slides.
Oh, the initial slide as an example of a character in the animation, was that represented using splines? No. It was a mesh which had the boundaries, which was computed as one of the techniques as non-photorealistic rendering, right? To be able to enhance the boundaries of the character. Right? So just the way perhaps those of you who are familiar with images, you can enhance the edges in an image, right? So here you want to enhance the contours of the model. And maybe because of the resolution of the mesh, which is perhaps adequate in this case, you still observe continuity or smoothness.
But it's possible to design the character.
Yes, this is very possible. Yes.
At the end of the day, the points between P1 and P2 will be discrete following these equations.
Yes, the P1 and P, they are all discrete. That's correct.
Even after doing a smooth cubic spline.
Yes,
So ultimately the representation or rendering will depend on how fine.
that's right. That's it. So there is also an issue of how do we render the curve which I have obtained in a continuous representation, right? So that could still lead to piecewise linear decomposition of it, right? Or it could be a query that any point which I want to render, where does it lie? Right? So yeah, so the rendering may still involve discretization step. That's correct. So how are we doing time-wise? 8 minutes. Okay, so so what I'll do is I'll shift a little bit. So because I actually gave you two categories, right? One was interpolation and the other one was approximation, right? So there's another category of specifying or representing these curves parametrically where the shape of the curve will be obtained by specifying certain information in space. However, it's not going to interpolate. Right? So one such example is Bezier curves. How many of you know Bezier curves? Not many. Okay. So Bezier curve actually is due to Mr. Pierre Bezier, who worked in Renault Automobile in France. So here, what's happening is that you specify certain points which are generally referred to as control points. B0, B1, B2, B3 are the control points. And as a specification of these points, you get a curve like this, which tries to approximate the shape which you have embedded in the specification of these points. Now, again, this parametric curve represented through the polynomial, right? And in this case, a Bernstein polynomial is used. Basically, what you get, a representation of this type, which is somewhat similar as you have seen in the cubic splines, where these are not the coefficients but the points, right? And these are the polynomial, okay, which are the Bernstein polynomial. So if you look at these polynomials, this is n choose I, t to the power I, 1 minus t to the power n minus I. Now they have interesting properties. So for instance, if I evaluate J00 for any t, it's equal to 1. J and it, they're all 0 if they are not one of these sets n 0 to n, and they all sum to 1. Okay. So basically, for t which is between 0 and 1, J and ITs are non-negative. So what you observe is the representation of the Bezier curve is a convex combination of these Bernstein polynomials. Right? Okay, so for a cubic case, so when I say cubic, basically I am talking about n equals to 3. Right? So these are the Bernstein polynomials, right? Which look like this. And eventually, this is what you see, the cubic Bezier curve, right? Which is basically a combination of B0, B1, B2, B3, which are the control points, as the blending functions used, these Bernstein polynomials, which I can further, right? So there is a small similarity, if you can notice, is that again you see P of t, which could be represented as a matrix. Matrix in the form that you have this, right, which is coming from the known Bernstein polynomial, and this, which is geometric information, right? B1, B0, B1, B2, B3, this is the geometric information. So the canonical representation of all these parametric curves and surfaces, which is in the form of matrix, is similar, right? You have a matrix which is a collection of what you know, and then there is some geometric information, right? So you can further compose this in the monomial form. And let me just give you an example. If you specify these control points, curve sort of tries to take the shape of those points which you have specified, right? So that gives you a tool to be able to design the shape of the curves, right? Okay. Now what I'll do is quickly shift to an alternative representation of the same thing before I take up the details of it, which actually is through what is known as DCAS-12. Okay. And in fact, it goes much before than Pierre Renault, right? So Pierre Bézier. So what actually happened? DCAS-12 observed that you can design Bézier curves as just a successive linear interpolation. So as we know, linear interpolation is something like this, right? We are all familiar with it. So what he says that if I take, let's say, 3 control points, B0, B1, B2, and perform linear interpolation onto the spans which are formed by these control points, right? So I obtain at some t a point B10. Similarly, for this span, I obtain the point B11, right, for the same t. So basically I get this, right? Now if I apply once again a linear interpolation onto the span which is obtained through the intermediate points, I get this point, right? So this point, in the case of having 3 control points, lies on the Bézier curve. Now, which is easy to observe. Now, if you look at, these are the polynomials you have, right? Which are nothing but the Bernstein polynomials of degree 2. Right? So this is a very simple construction. All you are doing is successive application of linear interpolation. Okay? So the two are equivalent, right? The DCAS-12 algorithm and the Bernstein polynomial form, which is given by Bézier. Right? But this is sort of neat and terse. Okay, so now let me look at some of the properties of Bézier curves. Okay, now one thing which you would notice is that in the scheme of its representation, there is a relationship between the degree of the curve I get, right, and the number of control points I specify. Right, what is the relation? So in the case of cubic curve, how many control points I had? How many? 4. Right? So if I have a quadratic Bézier curve, how many control points I need? Quadratic, degree 2. 3. Right? So the degree of the curve is 1 less the number of control points I specify. Right? So if I have 2 points, right? If I have 2 points, what kind of Bézier curve do I get? A line. Right? Okay. So now, in fact, you would also then appreciate that if I increase the number of control points, which in turn is increasing the degree of the curve which I get, right, also gives me, in a sense, the flexibility of the shape design which I can do. Right? From line which is going from 2 control points to a quadratic curve which is going to 3 control points, and you know that in a quadratic curve, I cannot have an inflection. You know what an inflection is? Right? So, in order to be able to have a curve which is, let's say, fairly wiggly, I need to have larger number of control points. Right? This is clear? having higher degree of curves, because the computation which is involved, right, it goes high, and in fact if I have to do any manipulation with this curve, things are more complicated, right? But I do see that there is a relationship between the number of control points I specify and the degree of the curve, and which in turn gives me the kind of form I can get, right, or the manipulation I can have. Now, just quickly going through the properties, the first thing which I observe from the examples which you have seen is that the Bezier curve which I design passes through the two endpoints, right? So it interpolates the two endpoints, right? It doesn't go through the other points, it's at the intermediate points, but it goes through the endpoints, and that can be easily verified, right? If I do an evaluation of what happens at t is equal to 0, right, then I see that this is equals to 1 and all the i's which are not equal to n equals to 0 gives me this, right? The evaluation of the Bezier curve at t is equal to 1, which is one of the end points, gives me this, right? That's easy to verify. Okay. There's another property which is affine invariance, in the sense that if I apply an affine transformation to the curve, right? So you know what an affine transformation is? So let me give you examples of affine transformation. So translation, scaling, sharing, rotation, right? So the transformation which preserves parallelism is a class of affine transformation, right? In the context of modeling. Of course, there are other ways to look at it. So if I apply an affine transformation to the curve, right, it is equivalent to if I apply an affine transformation to the control points and create the curve. Okay. So that may have interesting applications, right? Because you are actually doing the manipulation of the control points rather than the curve itself. Okay. The other interesting property is that the curve which you obtain resides inside the convex hull, right, which is obtained by the control points. Right? So if I have control points at B0, B1, B2, B3, then the curve P of t is going to remain inside the convex hull of the points B0, B1, B2, B3. So that's what it means, right? So the convex hull of this is this shaded part. Okay. So one of the ways in which you can look at convex hull is that if you take a string, and these are sort of nails, right? So if you wrap it around, right, the shape inside is the convex hull. So this is not a formal definition, but just for the purpose of your understanding. Okay, so it's also easy to verify as we observe that the sum of all these J and I's, right, which are the Bernstein polynomials, sums to 1, and all of them are non-negative, right? So it's basically a convex combination of B0, B1, B2, B3. Right? Now, let me also revisit the de-Castro algorithm and see how these properties get addressed from that representation, right? Because we have said that, we have established that both are equivalent, right? Well, if you look at affine invariance, it's easy to see. What happens? So de-Castro algorithm is nothing but sequence of linear interpolations, right? And if you, so linear interpolation by itself is an affine invariant, right? How can you verify that? take a line, right? Apply any affine transformation to the line, right? And take any point on that line, for instance, midpoint. Okay, you can place the midpoint on the affinely transformed line, or it is equivalent to applying the affine transformation to the midpoint. Right? So linear interpolation is a finite line, the transformation, right? So therefore, since it's a successive application of linear interpolation, it's going to give you that property. Similarly, convex surface. So when you are doing linear interpolation, all the intermediate points which you have, right, are coming as a consequence of convex combination, right? Because linear interpolation uses only convex combination, isn't it? So therefore, the curve which you are going to obtain would give you property of convex combination. Okay, so what the point which is being made here is that not only they're equivalent in their definitions, but all the properties you can verify for both the representations. Okay, time is up. Fine. So I think I will talk a little bit about surfaces in the afternoon, because many of these ideas which you have seen in the definition of parametric curves are easy to extend for the representation of surfaces, right? And if time permits, we are going to look at some of these animations, right? Otherwise, we will stop there. Okay, so this, now we are breaking for a pause, and after that, Professor Sharachandran is going to take over. Any questions if you have, quick one you can take, otherwise we will take them during the pause. Yes.
Regarding the voxel in the surfaces that you are creating.
Yes.
So one way of creating the surface is you have those planes on which you are trying to find out the contours, right? And then stacking the contours together to get the surface. But is there any other way by which I can create a surface directly from the volume?
Yes. There is.
The marching cube.
Marching cube, that's correct.
Is that the only algorithm?
Well, there are variants to my marching cube, but the basic idea is that it's the same. So basically, what are you doing there? Just the way you are doing it. Let's say you may be doing a contouring in 2 dimensions. Right? So given an image, if I want to figure out the contour, I may be doing somewhat similar to what I do in marching cube in 2 dimensions. Right? Now I can extend that idea in 3D and get the surface. Because surface, which is in that definition, becomes an isosurface, right? Satisfying a value in that volume gives you the boundary or the contour. Okay. Yes. So we can do directly in the volume. You don't have to do this separately on each of the images in the slide.
When you are referring to invariance, I mean, I understand invariance with something which is constant.
No, it's
So
basic. Is basically saying that it is invariance to affine transformation. So if I basically saying that if I apply an affine transformation, so what happens to the curve and what happens to the control points is the same.
But the midpoint of a line will not remain invariant.
No. It's an invariance to the transformation. So it's not an invariant property of anything, no.